Okay, guys, so we are going to start with one problem in the source-free circuit, although I did 3 problems already in yesterday's lecture that I posted, but let's do one more problem on this and then jump to the forced circuit like we did for the forced circuit for RC circuit. So let's go ahead and do one source-free circuit. Let's assume we have R1, 100 ohm, L, 2 Henry, R2, 220 ohm, R3, 330 ohms, and R4, 410 ohms. And let's assume this is a current source, 10 milliampere current source. Okay. And actually, that current source is going to be a step function because we want a source-free circuit. So I'm going to take it 10 U negative T milliampere. Okay. Number one. Determine IL T for T greater or equal to 0. ER4 at T is equal to, I'll come back to what time, since we'll have to calculate the time constant. I don't want to take a time that is going to be more than 5 time constant and then the power is going to be 0. So once we calculate time constant, then I'm going to put the time at which we want to calculate the power dissipated in R4. In the meantime that you're copying this, I'm going to put values in my MATLAB. And again, guys, do the same thing. Work with me here in Octave, MATLAB, whatever you want to use. Because again, if you keep saying that I ran out of time, that means you're spending a lot of time on doing those calculations that really you should not be doing. You can just use Octave to do those things. R1 is 100. L is equal to 2. R2 is 220. IS is 10 milli. R3 is 330. R4 is 410. Okay. Okay, so how should we start this problem? What we have to find? What we have to find first. Let's discuss that. We have to find the initial value of current passing through the inductor, because that value we are going to use to write down the equation when the source is going to be turned off. So how we are going to find the initial value of inductor current? Who's going to tell me? Say it again. It's not equal to. Okay, so think about it. IS is going towards that node, R2, L, and R3, right? It's gonna split. So that's not going to be equal to IS. Current division, as simple as that. Current division, right? L is acting as a short circuit. It will be fully charged before time t less than 0. L will be acting as a short circuit. So you have R1 on the left side and R3 and R4 on the right side. So you can apply current division simply. T at t is equal to 0 negative, let's say. Using current division, IL0 negative, which is equal to, let's call it I naught, which will be equal to IL0 positive just after the change is going to happen, is going to be equal to IS times R equivalent, that is equivalent of the parallel combination of R3, R4, and R1 divided by R1. IS times R equivalent over R1, IS times, where's R2? No, you don't encounter R2 because IS is dividing, between these two branches. IS is the current going through R2. And then it's going to go in this branch and then this branch. So you know the total current. Remember, current division is if you know the total current that is going into multiple branches that are connected in parallel, right? Then in any of that branch, the current is going to be the total current times the equivalent of all the parallel branches that are connected. Now, in this case, the parallel branches are these two branches, right? These two branches divided by that resistor value. So R2 in this case, it does not really matter because the same current is flowing through R2, which is going at this node and splitting between these two parallel branches. So you don't bring R2 in the equation in this case. I thought you said R2. No. Divided by R1. Your current division. So voltage division and current division, they're opposite, remember, right? Voltage division is, let's say VR4 is the total voltage across whatever resistance connected in series times R4 over R equivalent. And then the current division is, let's say IR4 is total current times R equivalent over R4. Now, the difference is this R equivalent is parallel and this R equivalent is series, right? That's the difference. So in this case, R equivalent is going to be parallel combination of R3 plus R4 in parallel with R1. Divided by R. All right, let's do that. So I naught is IS times the parallel combination R1 and R3 plus R4, R3 plus R4, and that divided by R1. 8.8095 milliampere, so 8.81, let's say 8.81 milli. And now we're gonna solve for t greater equal to 0. All right, when time exceeds 0, what is going to happen in the circuit? What change is going to occur in the circuit? Current source is going to be open. So current source is going to be gone. It's going to be open circuit. That means that whole branch is going to be eliminated. And therefore, we'll have a single loop with L, R1, R3, and R4. L, R1, R3, and R. That will be left. And our goal is to find ILT and the power in R4 at, and again, I'm going to decide the time once we calculate the value of time constant. PR. Okay, so what will be the expression for ILT for t greater than 0? What is the expression for ILT? Anyone? I naught E negative T over tau. A standard equation for a source-free circuit where the inductor is connected. I naught we already calculated 8.81. We need to calculate tau. So who is going to tell me? Well, so tau again, since I don't know if you guys looked at the lecture or not, tau is L over R. In this case, L over R equivalent. So what is R equivalent? Series combination of R1, R3, R4. So tau is L divided by R1 plus R3 plus R4. 2.38 milliseconds. So this is 8.81 e to the power negative t over 2.31 exponent negative 3 milliampere. That is the equation for the current. Milliampere looks like about 2.38. 2.381. Yeah, 2.38. 2.38 exponent negative 3 milliamp. So let's calculate power since the time constant we know now 2.38. So let's calculate power at 1 millisecond, which is less than the time constant. All right, who is going to tell me now? Yes, Chris, you want to tell me? Go ahead. Mm-hmm. Mm-hmm. Okay, so first evaluate the value of current at 1 millisecond, and then use that value to calculate the power I square R4. Very good. So let's do that. IL 1 millisecond square times R4. I naught times exp of time is t is 1 millisecond. So PR4 is I naught times exp of negative t over tau square times R. 13.73 milliwatt. 13.73 milliwatt. So once again, guys, solution should not take long. Analysis can take long. Even analysis, don't jump into applying methods and this and that. Analyze it. Sit down, look at the circuit, see what you need to get, how you're going to get it, perform the analysis. Solution, you can see that solution does not take long. It's very simple. Once you have the correct analysis, you have the correct equations, don't worry about solution then. All right, guys, question? Any question that you may have? Yes, Rudy. What time at which you are trying to find the power? That time? Which time you're talking about? So this equation is valid for time greater than 0. Yeah. You can put any time greater than 0, and you will get the current at that instant of time. Well, that's what we've been doing. We're calculating the response of the voltage of capacitor after it starts acting as a source. After time t greater than 0, it starts acting as a source. So first we find what is the capacitor voltage equation, and then you can plug in any time to get the actual value of the capacitor voltage in the circuit. In this case, it's inductor current. And again, if you want the inductor voltage, then we know the relationship between inductor current and voltage right here. You can apply this to get the inductor voltage. One thing, although, you have to be careful about, and I discussed that in my lecture that I created yesterday. This equation is when current is entering into the inductor and your voltage is positive here. When inductor is acting as a source, then current direction does not change, but the voltage direction is going to change. So if you're using this equation, make sure you put a negative sign over here, negative LdI over dt. If the voltage is changing, if you're trying to find what is the voltage equation, then you're going to use negative LdI over dt, because this equation is when the current is entering into the positive side of the inductor, where the positive polarity is. So it's charging. This equation is when the inductor is charging. But when it is discharging, you're going to put negative LdI over dt. Okay. And I did one problem in the one of the lectures that I created yesterday, and it's on Canvas, so you can look at that problem. But keep that in mind. Same thing goes for capacitor. We did a problem in the class actually. Same goes for the capacitor. That when you are calculating, I don't know what, so we calculated capacitor voltage. If we are calculating capacitor current, and if capacitor is supplying that current, so current direction is opposite, then you're going to use IC is equal to negative C dV over dt. If it is supplying the current, instead of it is being charged, it is giving up the charge. So you're going to use negative C dVc over dt. So keep that in mind. Okay, guys. So now we're going to move on. Since we don't have much time, we're going to move on to the discussion of. Let's just start with the new page. RL forced or forced circuit. Or complete response of RL circuit. So this is the same thing as what we discussed with the capacitor, complete response of RC circuit, or complete response of or forced RC circuit. That is, even after the change is happening at the time 0 or whatever your reference time is, you will still have some source in the circuit. The source does not go away. One source can turn off, the other source can come in, but you have the source in the circuit. So when you have that, then how you are going to figure out the response of the inductor current and inductor voltage. So complete response, as we did. And we use inductor current because, of course, inductor current cannot change instantaneously. Voltage can. So we start with the current You find the equation of current and then you can find the voltage, but it is true for voltage as well. You can do voltage if not current. It's just become a little more complicated if you're shooting for inductor voltage first, because inductor voltage can change in an instant of time. So the complete response of inductor current in a circuit where you do have sources after you're having some change in the circuit, complete response of course is comprised of the same, the steady state value and the natural response. Steady state value we calculate as the value of inductor current when time tends to infinity. That is when all the transients are gone and you're at steady state. And then the natural response is a e to the power negative t over tau. We have to find the value of a. So it is comprised of two parts, like we did for capacitor voltage, comprised of two parts. Capacitor voltage was a steady state value. When the time is running for a very long time, capacitor again is open circuit. What is the voltage across capacitor? In this case, if you're running a circuit for a very long time, inductor is going to become short circuit. And what is the current going through the inductor? That's the steady state value of the inductor current. And then the natural response we just discussed is a e to the power negative t over tau. And from the initial condition that we are going to calculate, we are going to find the value of a in that equation. So it's very similar to how we did forced VC or forced RC circuits. There we were finding VC first. Here we're going to find IL first, because VC cannot change instantaneously and IL cannot change instantaneously. So let's jump right into doing problems. Okay, let's assume that R1, R2, L, R3, and Vs. All right, so Vs, let's say, is 3 plus 2u. Okay, so let's say we find these two quantities, both for t greater or equal to 0. All right, in the meantime, you're writing. I'm gonna put values in my octave. All right, guys, if you look at the circuit, tell me what's going on here. Yes, there is. Question. So what I did, okay, so tell me how VS is going to be behaving. Tell me that first. But how it's going to be behaving? Chris, how it's going to be behaving? Oh, it is a voltage source, but how it's going to be behaving at different instances, different time values, what will be the value of that source? Anyone except how this source is going to be behaving, guys? 2 plus 3 plus 2 UT. How it's going to work? Yes, Natasha. Positive value of what? Positive value of what? T, okay. Right. 5. Very good, excellent. So as long as t is less than 0, the step function is not going to be on, so the value of Vs will be 3. And when t is 0 or greater than 0, then the step function will turn on, and the value of the source is going to be 5. So that's how their source is operating. So there is what you asked me how to write it. To know how to write, first you need to know what the source is doing. If you don't know how the source is behaving, what you're going to write? What I wrote simply, I divided into two parts. I divided into Vs1 is 3 and Vs2 is 5. So before time t is equal to 0, I'm just going to use my Vs1 variable. And after time t is equal to 0, I'm going to use my Vs2 variable. That's how I did. Right? Okay. So we have to find, of course, first thing we have to find is to find, since we are trying to find the current value, so we have to find the initial value of the current such that we can use that initial value to find the value of A. So let's go ahead and find the initial value of current. T less than or equal to 0, IL0 negative, which will be equal to IL0 positive. Let's call it I naught. Okay. So who is going to tell me how the circuit is going to behave before t less than 0, or before t is equal to 0, how the circuit is going to behave? And how we're going to calculate the initial value of current passing through the inductor? Yeah, that's what it means. If 3 means that it is running with the value 3, right? And then at t is equal to 0, the change is going to happen. So it is running for a long time with the value of source to be 3, and at t is equal to 0, we're going to have the value of source change to 5, from 3 to 5. Okay. Very good. So if before t is equal to 0, of course, inductor is fully charged. It is acting as a short circuit. And when it acts as a short circuit, it's going to eliminate R3 and R4, which will be parallel to the inductor. That means all the current supplied by the source Vs is going to go through the inductor. And how are we going to find that current? Rudely, how are we going to find that current? Yeah, because if it is running for a long time before t is equal to 0, then inductor is going to be fully charged. It will be acting as a short circuit. Okay, so how are we going to find that current that is passing through the inductor? We are trying to find the current passing through the inductor, initial value of current. How are we going to find that current? All right, Jose, how are we going to find that current? Use Ohm's law, very good. So what will be the equation? V over? Vs over R1 plus R2, very good. So you simply use Ohm's law. Since all the current is going through the inductor, then it's a single loop circuit. We use Ohm's law to calculate Vs over R1 plus R2. Inductor is fully charged and short. Okay. So that's my I naught is equal to Vs1 divided by R1 plus R2. So 20 milliampere. 20 milli. So that's my initial value of current. Now we're going to analyze the circuit after the change is going to happen. Okay, so analyze the circuit, analyze, let's say IL. After the change is happening, we need to find out the steady state value. And then the natural response equation is going to be this, and we'll have to find the constant value A. So first, the steady state value. Who is going to tell me? IL steady state. Looking at the circuit, how are we going to find the steady state value of the inductor current? Again, a steady state means it's running for a very long time. As time approaches infinity, what's going to be the value of the inductor current? Yes, Chris? No, don't give me the result. Tell me how you're going to calculate that. Okay. Five-volt current plus what? I'm sorry. Plus N plus A. You're not understanding. I'm asking you, what will be the current value in inductor if the circuit is running for a long time? That is, you keep running the circuit after t is equal to 0. How are we going to calculate IL? Don't give me the result. Okay, this is the value. Tell me what's going on and how you're going to calculate it. Mike, how are we going to do that? T greater than 0 running for a very long time. T is hitting infinity. What's going to happen in the circuit? How are you going to calculate the current passing through inductor? I'm sorry? Yeah, Vs is going to be 5, yeah. No, don't give me equation. Tell me how the circuit is going to be behaving. First, establish how the circuit is going to be behaving. as time hits very large value, how the circuit is going to be behaving. Yes. Current goes towards them? Yes, Natasha. How the circuit will be behaving as time keep getting bigger and bigger. Yes. Sure, acting as a short circuit. Yes, so exactly, and that's why I'm amazed that you guys. Yes. Then how? What will be the current in the inductor? Yes. Huh? Combination of what? Didn't we just do that? Where did Gloria go? She left. Why? Okay. Should have asked her why she's there. Yes. We just did that. Inductor is fully charged and short. That's before time t less to 0 when it is running for a long time. Now it's the same thing. T greater than 0 running for a long time. Inductor is going to be fully charged at a different energy level and it's going to be short. So your steady state value is going to be the same equation except Vs is different. It's 5 volt. I have bad vibe about what the result is going to be in this class, to be very honest. Here it is 3 volt and then it is 5 volt. $33.3 milliamp. That's why I cannot solve more than 2 problems in the class. That's sorry guys, I'm trying my best. Okay, so it is a steady state value. So we found the first part. Now we know the second part is going to be a plus e to the power negative t over tau. We need to know what tau is and we need to know what a is. Now ILT is IL steady state plus. Okay. To find the value of A, what we used to do for the capacitor circuit, RC circuit, because the equation is the same, except it's voltage, here it's current. Yes. That's not the answer of what I'm asking. What do we do to find A? Don't tell me the equation. I'm telling you just the process. What is the process to find A? What did we used to do in RC circuits that we already discussed last week? Last week or this Monday? That's not the answer. What's the answer? Again, that's not really the answer. The answer is we evaluate this equation at t is equal to 0 positive at the initial condition. We evaluate the equation at the initial value of the inductor current. So at t is equal to 0 positive, IL0 positive is ILSS plus A, because when you put 0 for t, 0 positive and 0 same. When you put 0 at t, exponent value is going to be 1. So you evaluate the equation at the beginning of the time. And we know what is the initial value. That's why we calculated the initial value of current in the first place. I naught, 20 milliamp. So A is equal to I naught minus IL steady state negative 0.013, so negative 13.33 milliampere. Okay, who is going to tell me what will be the time constant of this circuit? How do we calculate time constant of the circuit? What is the process? I'm sorry? That's a formula. What's the process to calculate the time constant from this circuit? Yes, Chris. I'm sorry? R4 and 3 in series, okay. Okay. Okay, so in this case, not times inductor, it's L over R. But yeah, you're right. So to calculate the time constant first, the circuit has to be natural circuit. So you remove all the sources. So you're going to remove Vs. You're going to short it down. And then you are going to calculate the equivalent resistance across the nodes where the inductor is connected. So that's going to be, as Chris said, R4 plus R3 in parallel with R2 plus R1. So L divided by that equivalent resistance. Not R4 parallel to R3, R4 plus R3. R1 plus R2. R1, R2, and R3. Okay, that's going to be time constant. Let's calculate that. How is L divided by parallel combination of R3 plus R4, R3 plus R4, R1 plus R2. 33.797 or so 33.8 milliseconds. So our final expression for the current is ILSS is what? 33.3. 33 point ILSS is 33.3. 33.3 minus 13.33 e to the power negative t over tau, which is 33.8 millisecond milliamp t greater or oh, I'm not saving it, really. It's not good. That's not 6 Wednesday 02 12 2020. And from the equation, you can plug in the value of t to make sure that you're getting the initial value of the current. So when t is 0, then it's going to be 33.3 minus 13.33, which will be 20 milliampere. And that's the initial value of the current at t is equal to 0. Just to check that your equation is correct or not. All right. Good. Question, guys. Any question? And again, guys, you have to solve this problem. Remember, you have to solve this problem. You cannot just rely on we are doing it in the class. If you're not going to solve it yourself, you're not going to learn. Yes. Yeah. Yeah. What? About what? Explain what? Oh, A. So A in the A constant in this equation. So this is our generic equation right here. This is our generic equation. It has two parts. It has the final value of current, which is the steady state, plus the natural response. Now, this is not the initial value of current. If it's the source-free circuit, then A is equal to I naught. A is just a constant value that we have to find out, but we still need the value of I naught to find that A. So in this equation, basically we evaluate this equation at t is equal to 0. So on the left-hand side, when you put t is equal to 0 or 0 positive, that gives us the initial value of the current that we found out in the first part. So that's I naught at t is equal to 0, left side. And the right side, you have the steady state value that we calculated, and E negative 0 will become 1. So you're going to have initial value equals final value plus A. And from that, you can calculate A is equal to initial minus final. Yeah, exactly. So that's how you're calculating it. Okay, so this is ILT for t greater to 0. Now, how are we going to calculate from the circuit? How we are going to calculate the voltage across R4? What do you think? And if you answer incorrect, I'm okay with that, because it's not as simple. Well, it is simple, but since you have inductor and everything, it might not be the same answer. But if someone can tell me what you are going to do to calculate VR4. Mm-hmm. Mm-hmm. Excellent. That's what I was looking for. So we know the current expression. We know that voltage across inductor is LDI over dt. We can do the derivation. We can take the derivative of that current, calculate VL, and that voltage is going to be in parallel with the series combination of R3, R4. And then we can apply a voltage division to get VR4. Excellent. Now, in this case, since we have source and source is supplying current, the voltage is not really changing the direction. It's still going to be VL. Because it's not, it's just the level is changing from one energy level to the other energy level, but the source is still supplying the current. So we will still go ahead and use this equation. If the voltage does change the direction in the source-free circuit, as I said, then usually we're going to take negative of LDIL over dt. But in this case, we're just going to take LDI over dt. So let's go ahead and calculate inductor voltage. All right, when we take the derivative of this, what will be the result? I'm not going to write the whole equation. I'm just going to write the result. Who's going to tell me? Derivative of inductor current. Okay. 13.33 over tau. Okay. And milli. So remember that's milli. So I'm going to write down in terms of 0.0133 to compensate for this milli. I'm sorry. Right. But I'm just putting tau. So I'm not doing further calculation in my MATLAB. I'm just going to use this and then put it in there. And E minus T over tau. So that's going to be the derivative of that. So when I calculate the constant value, that's going to be L times, what is that? L times ILSS, right? That's ILSS. No, that is my A. Yeah, that's my A. So L times divided by tau. 1.5871. 1.587 e to the power negative. Therefore, VR4 is VLT times R4 over R3 plus R4. So that's going to be B times R4 divided by R3 plus R4. 0.987. 0.9873 e to the power negative t. That's what we're looking for, right? Voltage across R4. Yeah, voltage across R4. So that is what I'm getting. I'm sorry?
So is there a reason why we wouldn't evaluate this further?
I did not ask anything beyond that, right? And it depends on the question.
Oh,
In the question, I'm asking only to calculate ILT and VR4T for t greater or equal to 0. So if there's something else that is asked in the question, then yeah, you're gonna go ahead and work for those things as well.
Well, I just meant like the negative t would be 0 anyways, but
Negative t will be 0. What do you mean? What do you mean by that?
so you said greater than or equal to 0.
Yeah, this equation is valid for any time after 0.
Oh, right.
Yeah, this is just an equation valid for any time after 0. So you can plug in any time and then get the result.
So I'm just asking as the understanding of to leave it like this, it's okay because I would.
That's what it is asked in the question, right? VR4 for t greater or equal to 0. So this is VR4 for t greater or equal to 0. If it asks you what is the voltage at 10 millisecond, then you're just going to go ahead and plug t is equal to 10 millisecond in this equation and give the final result, right? But they're just asking you what is the t greater or equal to 0. That's an expression. It's not a single value. It's an expression. You can get any value from that equation or expression at any time instance. All right, guys, any other question that you may have? All right, so what are the steps if for the forced response of either RC circuit or RL circuit? What is the first step that you have to take if you're solving for, let's say, inductor current in a forced circuit where the source, whether it's a voltage source, current source, whatever, the source is not going down to 0 at the change? What is the first step that we do? Yes. Voltage node is what connected to? No. Yes. What is the first thing that we do? The what now? Find the initial value of the inductor current. Very good. Find the initial value of the inductor current for t less than 0 or t is equal to 0 negative, basically. What is the second thing that we do? Again? We find the current of the inductor as that's after time t greater than 0. We find the current value when it will keep on running, circuit will keep on running, and inductor is saturated. What value of the current passing through the inductor? That's the steady state value of the current. All right, then what do we do? What, say it again? Right, but we have to find the time constant as well. So we find time constant, or we find the value of A first, but time constant doesn't do anything with the value of A. So the third thing that we do is we find the constant A in the equation by evaluating the equation at the initial condition. And then find the time constant. So these are 4 standard steps. So these steps are really not changing as long as your goal is to find the inductor current in RL circuit, or if your goal is to find the capacitor voltage in RC circuit, right? These steps are the same. Where you're going to make mistakes is how you're evaluating the circuit. Again, analysis is important because these steps are not going to change. You have to find initial current first. So you have to analyze the circuit to see what parts of the circuit are going to be removed, what parts of the circuit are going to be there, how the resistors are going to combine, all those things. And then you're going to decide, okay, now what is the value of current in inductor? So analysis, that's why I keep emphasizing on the analysis, because again, these 4 steps are standard steps. They're not going to change. Solution is very easy. You put the values in MATLAB and you write the equation, you get the solution. So those things are very easy. Analysis is what you have to learn, guys. And that's what, except a couple of us students, nobody is learning so far, as how to do analysis. And it's almost half of the semester is coming to end. And this analysis is not difficult, like series parallel circuits and stuff. You guys are struggling to observe that which things are connected in parallel, which things are connected in series. I mean, that struggle shouldn't be there actually at this time, at this stage, advanced stage. All right, I don't think we can do any more problems. Again, what I can do is I can do a couple of more problems and then add to this, which I will. And that's what I'm going to do actually, because again, we don't really have time. So what I'm going to do, I'm going to go over real quick lab, because I'm going to pause the lab and then let me discuss the lab real quick with you guys. So let me save this first. Okay, so that's lab number 2. Lab number 2 right here. Yes.